Thank you. So welcome back to a new lecture. Today we'll be looking at how to build an application using the models available in Roboflow. And we will also see how to deploy it. So in the last lecture, we had discussed a brief introduction to Roboflow and its features. What all can we do? We also tried as a group trying to annotate images together for training it. In this lecture, we will be using a pre-trained model, but we'll be deploying it so that anybody could use it. So I also want to show you one thing which you might be interested to see from Roboflow. So the Roboflow has this thing called Roboflow Universe. So if you go to this website, universe.roboflow.com, and if you scroll down a little bit, you should see a section called popular categories. So click see all, and here you can see different domains in which you will find computer vision related data set and models from Roboflow. So this is spanning almost everything you can imagine. The good thing is, for example, if you want to, let's say, click aerial domain, it will open models and data set that are annotated, which are created by other people, available public. So let's say I go to this energy aerial data set. Here, these are some data sets. Some of them might be about oil fields. Some of them might be about electrical substations, windmills, etc. It shows how many images are originally present in the dataset, which will be augmented by random rotation, random cropping, etc. So training dataset will be much bigger than these number of images. And by reading this annotation, so here you see an annotation called model is there, which means it's not just about the dataset, it also contains model. So if you click this, you should see the dataset here. If you click the dataset, you should see the annotation. So see this. These are all annotated data sets. So these bounding rectangles have been assigned already by the person. So these are about insulator classification, broken insulator versus normal insulator. There are many different problems. And then the model, if you want to use, you have a model here. Since this is an already trained model, you can directly use it. So if you have a video of, let's say, electrical systems, you can just upload the video here by clicking select file, which I will show you today. But here I'm just showing you the example. And you can draw inference on that particular input which you give. These are test data sets on which input is being inferred. So see, this is getting the predictions. And here is the predicted bounding box. And here are the exact coordinates, x, y, width, and height of the bounding box, plus the class ID, the confidence, object confidence. Today, what we'll be doing is something very specific. So in the second part of today's lecture, I also want to discuss about the hands-on projects which are part of the course for pro students. But today we'll be building one such hands-on project for detecting falling by elderly. So when elderly people are walking, falling is a very big hazard, because if they break the hip or something, there is a very high chance of them being bedridden, muscle atrophy. Then it's very likely that they may not walk again. So falling is something that you have to prevent. Or if it happens, some help need to arrive immediately. And if these elders or whoever is facing such incidents, if they are in a space where some CCTV or some kind of footage is available, we can build good real-time detection systems that can predict the falling event from happening real time. So I first want to show you what we are going to build, and then I'll show you how to build it. So what we are going to build today is something like this. So this is Streamlit. It's a publicly hosted link. If you go to this link, you can also open this. And here, this confidence threshold is a parameter that we can set for deciding which bounding rectangles we need to identify from the inferring video or inferring image. So here I'm going to select the option of uploading the video, and then say I browse the file and I upload a video, maybe this. So here now I have given the input video. A model is running behind this. I will show you exactly how to build this, but just see the final output. That's what I want to show you. And this is a video which is taking a bit of time to process. You can see that it's being processed frame by frame, not real time. And I'll tell you why that is also happening, because ideally we want real time processing. But this is anyway not a model that we are hosting ourselves. It's hosted on Roboflow. That's why it's a bit slow. But now you will see a bounding rectangle coming as soon as the person is detected with a certain confidence score. There are two classes for the objects that are there in the bounding box. One is stand, another is fall. So if the person has fallen down or is falling down, it will show fall. Sometimes it can cause mistakes, but you'll see in a moment that as soon as the person slips and falls down, it shows the fall has happened with a certain confidence score. This video, the way this Streamlit app is set up is in such a way that you can also download the annotated video at the end of processing. So this video is only very short. It's only 7 seconds. So only around 150 frames. But see here, once the video processing is finished, you can see this annotated video and you click that, the video will be downloaded, and the downloaded video with the annotation, you can open and just play it. So this is the annotated video. All right. So what we are going to build is exactly this, so that you can run this on pretty much any input and you can get the corresponding annotated output. Annotated output is anyway a fancy thing. You necessarily don't want annotated output always in real time processing. You just want to detect. Once the detection is there, whether you annotate or not is secondary. But for showing it to someone else, annotation is very helpful. So the software which we are going to be using is obviously first is Roboflow. So Roboflow is where we will find our data set with annotation and model that is pre-trained on this data set. So pre-trained model. Then we have a few different options. We could host the model on Roboflow itself, which is definitely fine. But instead, what we are going to do is we will use the model using its API and write a custom code in Visual Studio Code such that we can initially draw inference on our local computer itself. So this will help us have inference locally. And I will then also show you how to convert this thing into a Streamlit application so that we can host it publicly. And this is when things become actually useful. Right? So these are the three things that we are going to do. And obviously hosting is done using Streamlit. So Streamlit is an application where it allows you to host Python-based applications very fast. So I'll go through this step by step. First thing, go to Roboflow Universe. So universe.roboflow.com. And in this section, so I'll just zoom in a little bit. In this section, type fall detection. When you type this, it will open different set of projects. So you can see that the number of images in different projects are different because it's done by other varying set of people. But what I have found is this particular data set has 7,100 images, which after augmenting, it can be much more because random cropping, random flipping, all those operations can be done. Now, this is the data set. We are not going to directly download the data set, but here is the pre-trained model. So this model is already trained on this particular data set. And you can see that some predictions are being made. But there is a mistake. This model, what it's actually predicting is when a person has fallen down, it's annotating that they are standing. But when a person is actually standing like this, it shows fallen down. So the model accuracy is very good, but I think what has happened is somehow the annotations they have flipped by mistake or something. So we'll see how to fix that issue, but the model is good. How do we know it's good? Because mean, average, precision, and recall, they are all good. It's a reasonably big data set, probably one of the biggest in Roboflow. And it's working very nicely. And these are the sample test data sets. Now, how do we use this particular model for our use? We could use it directly from Roboflow itself. So if you want to find whether a person has fallen down or not on an image, let's open the falling video. So let's say this, or rather, let's say this is our video and the person has fallen down, and I take a screenshot of this, and we can try uploading this screenshot here, or we can upload the entire video itself. So I just uploaded it here, and right now it's inferring, but there are no predictions. Maybe I have to reduce the confidence threshold a little bit. So I'm just reducing it to see if any rectangles are appearing at all or not. Looks like the model is finding it difficult to make predictions on this particular image. Yeah, the model is actually finding it difficult to make predictions on this image. So what I'll do is we can also upload the video instead of this file. So click this. Upload the fall.mp4 video. And then you will see the model annotations. I have decreased the confidence threshold. Now what's going to happen is even some useless rectangles are going to appear, which we can make disappear by adjusting this confidence threshold and overlap threshold. But let's see the inference. So here loading the model means it's processing frame by frame. And it should take only a few seconds. And while that is happening, let's also discuss why this is not very useful. The reason why it's not very useful is because this is in Roboflow platform. It's not under our control. We can't custom change some parameters, and we can't get it in a format that we like, right? That's not good. See, this is what the model is doing inside Roboflow, but there are mistakes. Standing is shown as falling, falling is shown as standing. So model has flipped its output. So what we do is we figure out how to use this model, but not from Roboflow, but from elsewhere. So what we can do is scroll down, and here you can see different options. Either we can get this hosted API. So basically we access the same model by having an API call. So this is my API key, which obviously I'll be deleting. But this is the hosted API. Or if you want to infer from your own device, like your computer, you can get a code for installing the Inference command line interface. And then using this command, we can use it on any image. So what I'm going to show you is how can we use this particular model. This model name is anyway random. It's given by the original author of this particular project. Name can be whatever, but how to use this model, because it has good accuracy. How to use this model for our purpose. So let's go to Google. Let's go to Visual Studio Code. And I have already written the code where this can be done. So what I'm going to do is I'm going to walk you through this code first, block by block, and then we can discuss how to convert this code into a Streamlit application. So let's create some space. So first we are importing the required library, importing request, and CV2 is OpenCV. Then we have some configurations to be set. So first is the Roboflow API key. Second is the Roboflow project ID. So project ID we can get from over here. See, this is the project ID, fault detection MBL DH. But we don't have to copy it from the URL. We can get it from here itself. In this hosted API section, we know the project ID. The project ID here. And we know the model number is 1. We know the API key. So I have, instead of using this code directly, I have converted it into a bit more usable format. So API key, project ID, and model version. The next thing is we have an inference URL. Basically, we are calling a Roboflow URL with given project ID, given model, and given API key for performing inference on our input data set. And what is the input data? Input data could be an input video, or it could be a stream from camera. So it could be webcam, CCTV cam, or input video, whatever it is. And output video, we want to store the annotated version for our own just visual. We want to just see how it looks. Confidence parameter is an extra parameter which I have added so that we can play with it in case the output is not good for the default confidence threshold. Then we have a function defined so that frame by frame, we can run this function to get the inference for that particular frame from Roboflow. So each frame is passed to this function, and each frame means it's an image, but it's encoded into JPEG format before we send it for inference to Roboflow. And where is the inference happening from Roboflow? In this line. So we are sending a post request to Roboflow API, and Roboflow API is defined up here, API key is defined up here, but this is the URL. So that URL we are passing here, inference URL. And the files that we are passing is the JPG encoded image. And this is the data. Now, if the prediction on this particular frame is successful, which is when we will get from the API a response JSON, response status will be 200. Then we convert the response, whatever is the response, into JSON format, and we just simply return it. In that response, if the inference is successful, we will have the bounding box rectangle coordinates. We will have the the object confidence score, and we will have a class probability. Otherwise, if the inferencing is not successful, we simply print an error. We don't return anything. Then comes the main part where, okay, inference is anyway done by Roboflow. We don't have to do anything. But once the inference is done, once we get the rectangle back, we want to write it into our current frame. Write it meaning we just want to superimpose it. So this is where we are capturing the video from the input video file. So input underscore video was defined here. Slips v2.mp4. So my folder structure is each lecture of the series I'm putting in different lecture folders. But this video, right, this slips v2.mp4 video is just outside it. So I have a parent folder inside which I have different lecture folders. And outside of all of that, as I can show you here. So this is my structure. So my code files will be inside this folder, in this lecture 10 folder, but videos will be outside here. And I have defined a local environment so that whenever I install new packages, it's confined to this particular environment. And now we have captured frames from this video. Now here, what I'm doing is I want to write the video into a format at the same resolution and same frames per second as the input. So if the resolution is 1024 by something, I want the same. If FPS is 24, I want the same. So I use a certain codec. So video codec defines, you might have seen sometimes while trying to play a video, codec error. This was very common, not with VLC media player, but with many other media players, it was very common because codec does not match. So here we use a certain codec. Here we get the frames per second of the input video. Here we get the width parameter in pixels of the input video, height of the input video. And then we say output video should be of this particular file name, this particular codec, this particular frames per second, this width, and this height. So that is how the output will be created. And then we start with the zeroth frame. And then this while loop ensures that we are going from frame to frame unless the frames have finished or we have manually quit the process by pressing the Q button. So that's why we have while loop. It has to keep running. So from our capture, so capture is this, capture is from the input video. We are reading frame by frame. So we have frame here. All the frames are available here. If frames are not there, we just break out of the loop. Basically, from the capture, if I cannot get the current frame, I break out of the loop. And this will happen if there are no more frames available or if the video has ended, right? Otherwise, we will not break out of the loop. And then if once I process the first frame, once I get the first frame, I increase the frame count by 1. And here is where we store the predictions from Roboflow. So infer underscore frame was the function. If you remember, this was the infer underscore frame function to which we are passing 1 frame at a time. And that passes to the image to the Roboflow API. And then you get the response. So that response or predictions we are storing here. But that predictions is in a specific format. As you might have seen here, this is the predictions format of Roboflow. See, it's like an object. And inside that, the key is prediction. Value is whatever is here inside this. Inside that, again, there are key value pairs. So if this predictions object does not exist, it means there is no bounding rectangle existing in the current frame. For example, check out this, perhaps. Check out this frame. Here, there is no variable called predictions. So hence, there is no bounding rectangle. But if you are over here, there is 1 bounding rectangle. And because of that reason, there is 1 prediction. So here, what we are checking is if this variable called predictions exist, and if a key called predictions exist inside this predictions variable, only then go ahead and process the bounding rectangle. That's what this if condition, this complex if condition is saying. And now how do we get individual predictions within this predictions key? So inside the predictions variable, I have the predictions key. What is that? That is this guy. So this is the predictions key, this double quoted thing. And inside the predictions key, I may have one or more objects in terms of bounding box. So I have to get them individually. So for pred in predictions means this pred will now be one bounding box rectangle. I get the confidence score corresponding to that. And where is the confidence score stored? It's stored as a key inside the pred. So this is the confidence score stored as a key. So I get this, and I have to check if this number 0.654, whether it is greater than or less than my confidence threshold. The threshold is defined up here. So I have to check if my confidence score of the current prediction is greater than 0.2 or not. If it is less than 0.2, I should skip. If it is greater than 0.2, only then I should annotate. So going down, if confidence is less than confidence threshold, continue, meaning I will not break out of the while loop, but I will continue to the next segment of the while loop. But otherwise, if confidence score is greater than or equal to the confidence threshold, then I go ahead with the remaining lines in this block. So then we extract pred of x. What is that? This is x in double quotes. That is the key corresponding to the x coordinate. This is the key corresponding to y coordinate. And then double quotes width is the key corresponding to, width corresponding to the bounding rectangle and height corresponding to the bounding rectangle. So here we are extracting pred of x, pred of y, pred of width, and pred of height. So we extract x, y, w, h so that we can now draw the bounding rectangle. And the class, predicted class, we extract and convert to lowercase so that we can compare whether the class, because as you see, this model has messed up. It has flipped standing as falling and falling as standing. So that we have to fix in our case. So the class we will get from this class is falling. So that also we extract. So now we have all the relevant info we need. We have confidence score over here. This variable has confidence score. These variables have the class name and bounding rectangle coordinates. Then we say if the class name is equal to fail, then my display label should be stand. Simply because this particular model we are using from Roboflow have messed up their labeling. That's the only reason. Otherwise, we will not have this entire if condition we will not have. Else, if class name is equal to stand, we convert the display label to fall with a specific color. So red color for BGR. So green color for standing, red color for falling. So in OpenCV, it's in BGR format, not RGB format. So this is red. 00255 is red. Usually it's RGB. So usually it is blue, but here it is red. Now we draw the bounding box rectangle for the current frame. So this is the current frame. In the current frame, we draw the bounding box rectangle. At center coordinate is x minus width mod 2. Width mod 2 means we convert the width into, the half of the width into an integer. Here we convert half of the height into an integer. And then we say whatever is the x coordinate of the corner, we have to add half of the width and half of the height to get the center. So that's what we are doing. And then actually xy is center itself, but here what we are getting is the I think the opposite sides of the x and y. And then we define the color of the rectangle, and then we define the line thickness. So we can increase or decrease the line thickness. And then the display label is nothing but this. This is the display label, stand or fall or nothing. So that is the display label. And then cv2.put text will add the text at a specific coordinate where we want to add the text. Then out.write of frame is simply we are outputting the video current frame, annotated frame into this out variable. Where did we define the out variable? Over here. In the out variable, we had mentioned the output video name, the codec, frames per second, width, and height. So into this particular variable, we are writing the current frame. So out.write of frame. And then this part I have added, this part, the cv2.imshow I have just added so that while running the code, we can see what is happening. If this is not there also, it will run perfectly fine. This you can add or not add, but I have added it so that we can see while running the code what's happening. And here, this break loop is just to, if you want to quit the running in the middle, you can simply press the Q button, it will quit. And then at this point, line number 112, we are out of the while loop. Once you are out of the while loop, the frame capture you release, the output video you release, and you ask OpenCV to destroy all windows, meaning it will close all the windows, and simply in terminal, it will print processing completed. So very simple code, nothing fancy is happening. Now let's do one thing. Let's first run this code and see how this works. And then we can go ahead with the rest of the thing. So input video was fall.mp4. And output video, I can just say some other version so that it saves as a new file. And then I start running. And when it is running, you should see frame number 1 being processed. So you should see the frame number mentioned here, processing frame 1, processing frame 2, etc. And that particular frame also you will see here, because we are outputting the current frame that is being annotated in the using CV2, using OpenCV. But this is just for our purpose. I mean, this is not mandatory. One issue you might notice with this model is clearly there is a person here, but the person is not being detected really well. Maybe because, you know, it's the limbs are not properly visible. This person is wearing like a big jacket. So totally there are around 150 frames in this, because this is a 7-ish second, 6 or something second video. So 6 multiplied by around 24, around 150 frames are there. So right now 1/5 has been processed. But you might notice the issue right now. The issue is, if you want to use this model, how will you use this? I mean, this code and this annotation, if you want to use it, you can't use it because I'm running this locally, right? I'm running this on my end. Now, if I want to use this, I want you to use this, I should host this somehow publicly. Now, there are options for hosting this in public on Roboflow itself, but the problem is it's kind of expensive depending on the number of calls you make. Here also you are incurring, I'm not sure how much this API is free, but I'm sure there are some limits. There are certain number of calls you can make to this API. I'm sure that exists. But in any case, whether you are using a paid plan on Roboflow or free plan, it will be very nice to have total control over your application that is hosted. Like, for example, this Streamlit, you have total control. You can decide whether you want this sliding bar or not. You can decide if you want to provide only the webcam option. You can decide if this download option should be provided or not. It's totally under your control. So what you have to do is let this video process. Meanwhile, I'll show you what to do for Streamlit. For Streamlit for deploying, you need to first have a GitHub repo. So go to open GitHub, and create a new repository. The name of this repository could be fall detection Streamlit. So this is a new repo that I'm creating, empty repo. I'll keep it public. So it's a public repo, anyone can access. Create repository. And once I finish creating the repository, I have to add the first file, right? So I have the habit of using GitHub desktop rather than using command line interface. So I'll open this in GitHub desktop. So now GitHub desktop is asking me to clone the empty repository. So I just clone it, okay? So once I clone this currently the repo is not ready yet because I don't even have a single branch in the repo. And don't worry if you don't know the terminologies of branch, repo, etc. I'm just showing you the procedure. I'm not trying to teach you GitHub, which is a separate thing itself, but it's easy. Now here I can open the corresponding folder. So if I open the corresponding folder in which the files are supposed to be there, this fall detection -streamlit is the folder. Now in this folder only, I should have the code for the Streamlit converted version of my current code. So my current code has nothing to do with Streamlit. But I have another version of the same code, of this exact same code, where I have also added Streamlit capability. So I'll just show you where the Streamlit is coming. So for example, in the Streamlit app, I have a title. So title is fall detection demo. Where do you see the title? This is where you see the title at the top, fall detection demo, Roboflow plus Streamlit. So this is a title, it's like an HTML. I mean, it's not an HTML page. I mean, this is an HTML page. The way we define it is different. Then what else I have? I do have a slider. So st.slider with the name of the slider and range of values and by how many fraction of that value can I change? So that will define this slider. Then I have two inputs, upload video and webcam. That is defined here. Options. There are two options. Choose your input source. With this is the option number 1 and this is the option number 2. Now, depending on which option I choose, this should show the corresponding thing, right? Because this browse file is available only for upload video. If it is webcam, I don't need the browse file. This has to pop up, right? So for that, I need to write two different conditions. One in case when I'm uploading the video, one in case if I'm using webcam. So this if option equal to upload video will take care of the uploading part. Else if option equal to webcam will take care of the webcam part, right? So two blocks. Now in this block is where I define this streamlit.file uploader. So streamlit.file uploader is this particular widget, this file uploader widget with this title, upload a video title. See, upload a video type equal to MP4, MOV, AVI format. Then if it is not suitable or if it is nothing, if nothing is uploaded, I have a if condition to handle it. Otherwise, I will simply send it to the processing to the Roboflow model. Or if it is webcam, it should create this click start to capture from webcam. So it should create this and it should start the camera input. As you can see, if I switch to webcam, it start the camera input from the browser and browser will ask me for permission. You give the permission and you can run it on camera also. So this is the only change that I have to bring on the code part for Streamlit. But now I have to add this to my GitHub. So what do? I go to my folder. In the folder, I have this Streamlit code. Then I paste that in the local folder of my corresponding GitHub repo. So this fault-detection-streamlit is the folder which I took from GitHub. So I paste it here. Now, after pasting, if I go back to my GitHub desktop, you will see that I have one change to commit because earlier there were no files in that folder. Now I have one file. So that entire new file will appear as a new change to commit. So I'm committing the change. And now when I push this change to my GitHub account, basically whatever was locally happening in my computer will now be there in the GitHub cloud. So if I now go back to GitHub, if I open the repo and if I refresh this, you should see this file appearing here. See, fault detection streamlit.py. Now this much is set up. Fine. Now we can go back to our code, the Streamlit code. So I'll go to this to open this particular repo file. So I have a .py file. If I want to open this in Visual Studio Code, there is a keyboard shortcut. On Mac, it is Command-Shift-A. So if I press Command-Shift-A, it will open that particular folder in Visual Studio Code like this. So I just open this in Visual Studio Code, then open this file. So this is now the Streamlit converted file. Streamlit converted meaning I converted the file which I was running locally into Streamlit compatible format. Now in the terminal, I can simply run this command, streamlit space run, then the file name, whatever is this Python file name, fall_detection_streamlit.py. So then I run this. And when I run this, you see automatically this localhost opened. So what's happening right now is Streamlit is hosting it, yes, but it is instead of hosting it publicly, it is hosting the model locally. So this is a local host, local server, which means no one else will be able to access. But this is not enough because I showed you that I told you that I'll show you how to deploy, right? So you can click deploy and click deploy now. Now, if while deploying, if this GitHub repo was non-existent, it will not work because it has to have a GitHub repo to deploy from. So here, now I can put some URL, detecting fall using computer vision. So this is my subdomain. The main domain will be .streamlit.app. Now I just click deploy. Now this model will get deployed. So depending on the size of the code, number of files, this may take some time. In my case, I thought it was pretty fast. It took me hardly 1 minute. Now what has happened is, see, one error has occurred. So the error that is occurring is this particular file in line number 1, import CV2, it's not available. So if you look at my code, I'm importing OpenCV, import CV2, import request, import Streamlit, import temp file, import NumPy. All these things I'm using. But where am I telling my code base that you have to install all these things? Because if Python has to be hosted in a server, that server should have all the modules corresponding to whatever imports we are making. So it should have an OpenCV module. Pip install CV2 should be done. Pip install Streamlit should be done. Pip install NumPy should be done. But where am I telling to do that? I'm not telling it anywhere. To tell that, I should add a requirements.txt file. So here I add requirements.txt. Inside that, I can mention which libraries to install. So here I have a proper requirements.txt file. So in this, I have these many things: Streamlit, OpenCV, Python headless, request, NumPy. So I just add these things to the requirements.txt. And when I make this change, obviously now I have to push the change to my GitHub. So now I have to go to my GitHub desktop. It will see that change. I have to commit this change because this requirements.txt file was not present before. So now this file is present. So I commit the changes. Or txt commit, and then I push to GitHub. When I push to GitHub, the amazing thing is Streamlit will automatically start the deployment because Streamlit is connected to that GitHub repo. I don't have to manually do anything. See, right now it automatically started building it because it detected that the GitHub repo has a change, and now it is working because requirement.txt will ensure that those packages, those Python packages are now being used. Now we can run this code file. So we can set the confidence threshold. And now I'll show you one more thing. What if I want to edit this title? If I want to edit, I can go to my code file, go to the part where I mentioned the title. Here I can say hosting the, let's say, fall detection model, something like this. Let's say this is my title. Now, how do I make this title appear in the actual deployed Streamlit app? Save this. When I save this, GitHub desktop will ask to push the change, commit the file, push the change. And once I push the change, it will appear on my GitHub cloud. And then Streamlit will automatically recognize it and Streamlit will change it. See, it's almost instantaneous. So this is how beautiful you can, publicly host the models that you built. So currently, I did not build any model. I used a already existing model. In the last lecture, we had already discussed how to fine-tune an existing model. The fine-tuning part is very easy. But here, I did not do any fine-tuning. Now, I can simply, if I want to use webcam, I open webcam, allow while visiting the site. So now my face is here, and it's not detecting me as person standing or falling, probably because, okay, I have to take a photo. So let me take a photo. Now, this photo will be used for inferencing. Okay, nothing is detected in this. So maybe I'll open a file in my phone, person falling. I'm just searching in the internet a file name called person falling. I mean, a file, an image called person falling. And then I open the webcam once more. So clear the photo. And in the webcam, I will show the image of a person who is falling down, something like this. This is the image of a person falling down. Click take photo. And see, now that has been detected as falling because the person it looks like falling down. So this is how webcam works. So if this webcam, instead of this webcam, it was let's say it was like a CCTV feed or something. So that feed, and now this application is hosted on a server. From the feed, it can click images. It can take specific frames. Maybe one frame in 10 seconds can be, or let's say one frame in 3 seconds can be analyzed. So instead of analyzing 24 frames per second, you just take one frame per 3 seconds. and analyze it for detecting falling or not falling. So that way inferencing will be very fast. Video inferencing is a little bit slow, as I showed you in the beginning. So if I upload a video, it will be a little bit slower than what you would like. So here I have uploaded a new video. Okay, so it's processing frame by frame, which is why it's super slow. I'll do one thing. I'll cut short the video a little bit. So this was the video. Okay, this person coming and just falling. So we want to see if this falling can be detected or not. So I'll just start from this portion where she is actually falling. So the video is super short. It can hopefully run faster. Version 3, and I go to my Streamlit. Okay, so Streamlit is processing it, but I don't see any annotations yet. I don't see any bounding rectangles shown yet. So maybe somehow this person is, now it is being detected. Now this person is detected as falling with only 47% threshold. So maybe the reason why this is happening is because of lack of diversity in the training data set of this original model. This video has one more footage where this person who is walking down is falling down. So right now you see this person actually has not fallen down, but before the person actually started falling down itself, the model showed that falling has happened. So in some frames, the model is missing to realize that the person has fallen down. See right now in the current frame, the model is failing to recognize, but in the immediate next frame, depending on the person's orientation, it's being recognized. So this is clearly lacking some fine tuning. We should fine tune the model a little bit more to make it work out really well. However, you should see, I had run this before. So I think in one of the soon coming frames, it will show the annotation. Right now, the problem is the person itself is not being detected. So, but pre-trained YOLO model is really, really good at identifying people. One more additional thing I can add here is a progress percentage bar, because right now I don't know how many frames are there. So if there was a progress percentage bar, I could know that, okay, 90% of the processing is done without having to wait. Right now, I know that it's mostly done because this is a small video, but waiting is not good. So this is what Streamlit is about. I'll close this and I'll upload the smaller file just to show you the downloading aspect also. So go to the desired file that is very small. Slips v3. Okay, this is very small. Yeah, and then execute it. So see, in all of these frames, the model is totally missing it. Model is not seeing that the person is falling down. Now it has worked. So this is the inconsistency with respect to model. So if you are building a model for actual deployment for production level purpose, obviously fine tuning is needed. That is the conclusion from this. You can't use pre-trained models with zero fine tuning. And how do you do fine tuning? Very easy. You get data set from various sources. What would be your data set? Your data set would be ideally videos. It could be from YouTube or elsewhere. And then Roboflow will allow you to chop the video into frames, which we discussed in the previous lecture, and use that frames, annotate it. For annotation, you can do it yourself or with the help of your team. Roboflow allows that also. Or Roboflow themselves, if you pay, they have an annotation team. And then once it is annotated, pick any already trained model and fine tune on top of your data set. So you have to choose the point from which you have to start. Sometimes you start from the random weights. Sometimes you start from the pre-trained weights. So you have to start from the pre-trained weights in this case. Okay, I think right now the processing has stopped because we are making too many calls to our API. I don't think we have a proper paid plan, which is why it's not working. But normally, if the model is hosted by yourself, it can run fast very well. So this is how you build a model, or rather fine tune a model and deploy it for your own purpose on Streamlit. You could also deploy it on Hugging Face. You could also deploy it on Roboflow itself. But I chose to show you Streamlit because it's very easy. It's connected to GitHub and changes are very easy to be pushed, right? So you could be still working on Visual Studio Code, but final output you can see on a publicly hosted link. So this link I will share with you. Feel free to play with this. I'm just putting the link in the chat. Now, one more thing which I want to discuss today is about the hands-on projects. So there are 5 hands-on projects which we had planned for this course. So after discussing about what is the idea for these hands-on projects, and this is only for the pro students, we can wind up today's lecture. So the hands-on projects are structured in the following way. I have divided it into 5 domains: physical security, agriculture, industry, traffic, and retail. These are actual use cases where I know startups working in this space who have raised $20 million in funding in physical security, agriculture space, and industry space. So these 3 I'm very, very familiar with. In traffic, you already know that there are AI cameras everywhere, especially in India. If you travel, if you don't wear seatbelt, you will soon get a fine to pay. In retail, there are applications where if you have a shelf which is empty, you need to recognize it real time so that the shelf space can be maximally utilized, right? So these are the 5 domains. So in physical security, the problem is if you have a crowd, counting the crowd and monitoring the unique ID of the people who are entering and going. So basically, the people who are coming and going can be the different set of people. So there is a incoming door and there is a door through which people go out, right? So it could be that. In agriculture, it could be to identify different types of crops, or it could be to identify crop versus weed, or it could be to identify disease in a certain type of disease in a crop. So healthy leaf versus not healthy leaf. In industry, there are many applications. It could be like whether people are wearing safety helmets or not, PPE kit or not, or if you have a conveyor belt counting the items. So here I have defined conveyor belt counting as a project for you. For traffic, in the course, we had discussed one problem with license plate detection. So that I had shown the implementation. So I removed it from the project. And here I have added instead seatbelt and helmet detection. And for retail, for now it's simple: empty versus stock. Later it can be extended to empty versus which specific items are stocked, because there will be n number of items in a shop. So these are the project names. But now here is what you're expected to do, right? So first you have to start with raw data. Data you can find from YouTube in the form of videos. Or Hugging Face, there are enough data sets. Roboflow has a lot of data sets. Kaggle also has a lot of data sets. So you find the data. The good thing is in Roboflow and Kaggle, you will find annotated. In Hugging Face also, you will find annotated data sets. Whatever you get from YouTube will be raw. There will be no annotation. But if it is not annotated data, you can use Roboflow to do the annotation. If it is an already annotated data, you can directly upload it to Roboflow and it will automatically recognize the annotation. Then for pre-trained model, you can find them from Hugging Face, of course, but you can also use Roboflow Universe for pre-trained models. For all the above mentioned projects, there are models in Roboflow Universe. For fine-tuning, you can definitely use Roboflow itself, which we had discussed in the previous lecture. So basically, you use a model, use its pre-trained weights, and fine-tune it on the current annotated data. For testing also, testing meaning I showed you today, testing with a random image or with a random video, that you can do on Roboflow. But at the end of the day, I want a deployed model which is accessible through a HTML link. So it could be hosted anywhere. Hugging Face, Roboflow, Streamlit, doesn't matter. I like Streamlit a lot, so you can try with that. But basically what I'm expecting is a deployed link. And for each of you, the expected deliverables are the following for each project. I'll show you first the 4 things I'm expecting. One is a teaching assignment. I'll explain what it is. Second is code. Third is a 1-page report. And fourth is the live deployed link. So teaching assignment is nothing but, Richard Feynman has a saying, when you teach someone, you understand something at the deepest level. So here the goal is not for you to come to the lecture and teach. It's just to create a 10-minute or max 15-minute video using loom.com. It's a very nice software for creating a video which shows your face and the screen recording, where you walk through what is the problem statement, what is the model / solution that you're proposing, what is your methodology of implementation, and then you actually implementing it. So these 4 things should be clear when somebody watches your video, and that you have to submit. Code submission, you can go do via GitHub or Hugging Face or Roboflow, anywhere, so I don't mind. In the PDF report, what I want is the model evaluation. So you will have to fine tune the model, which means the mean, average, precision, then precision and recall. These 3 parameters will be there. So you will be judged based on this. And finally, a live deployed model link so that I can test it with my own input. Now, the timeline for this is, I have defined it to be September 25th. The reason is, once you work on one project, right, it should be relatively easy for you to work on remaining projects, because the project workflow is the same, although you will be using different data sets and different models. So you can consider these as 5 different projects, of course, but at the same time, then your workflow should not differ from project 1 to project 5, which is why I'm not giving you 5 weeks. I'm giving you slightly more than 1 week. So I'll be evaluating your submissions so long as it is submitted on or before September 25th. Now, here are the evaluation criteria. Each project carries 20 score, 20 as the marks. So total marking will be in 100. And my evaluation criteria will be the following, the rubric. For each project, for teaching assignment, it carries 7 out of 20. Because here you will be forced to explain in a manner in which others can understand what exactly have you done. Then for the model metrics, I have only given 4. The reason is, even if your model fails to give a very good mean, average, precision or something like that, I don't mind it too much, because I know that depending on the data set that you're using, depending on the problem statement, this part can be tough. So I am only giving it 4 out of 10, 4 out of 20 as the weightage. Your code repo and the code has to look very clean. So 4 out of 20 goes for that. And giving me an actual functioning deployed link will carry 5 out of 20. And like this, 7 plus 8 plus 5, this will be the score for one individual project. Like this, there are 5 projects. Okay, so I hope that is clear. Now, what will you get as a pro member? So lecture videos, I have uploaded all the videos except today's. Today's also I'll upload. Handwritten Miro notes, I have uploaded all except today's, which I will do. Code files, I have pushed to the private GitHub repo, which all the people in the Discord should ideally have access to. If somebody did not get access, just put your GitHub handle in the Discord. Then you should have access to the Discord community server also. Then the other thing which I haven't given you yet is the hands-on book, which covers these 1, 2, 3, 4, 5 topics. I'm still compiling it. Some parts of the chapter and some figures are still being compiled, but you will get it ready by the end of the month. The 4th is project evaluation. So whatever your submissions are, I'll be evaluating it by the deadline. Then next is the code base, which I myself have developed for the same project. You will have access, but this access you will not get before your submission is done and before it is evaluated, right? So this you will get only later. And once you finish this, we will also be giving you a program certificate. So this is in a nutshell. There are a couple of questions in the chat. One is the name of startups working in these domains. So some startups are these. One is Hakimo, check this out. Another is Axen, check this out. And another is Detect, check this out as well. Not Detective, Detect. And then there are some other startups also called, what was it called? I forgot the name of one startup, which I literally ended up seeing yesterday on LinkedIn. I thought they were doing interesting work using computer vision. Just check out these startups. They have some amazing things going on with respect to planned leaf monitoring, and they have huge rounds of funding. All right. So, and last thing, I think I mentioned everything here. Yeah. So Shivam is also asking if we can extend the project deadline by September 30. I think I can do that, Shivam, but the problem is it will be too late. I fear like most people will not utilize the extended timeline. So I will not be able to extend it. But if for any reason personally, if you have any a tough week or something due to which you cannot submit by the deadline, you please message me personally. We can discuss the extension. But otherwise, normally for the batch, there will be no extension. Deadline will be September 25th. So with that, we can wind up today's lecture. Thank you so much. I will be getting back to you with some feedback. I need some feedback from your end. And we also have one more bootcamp starting called Transformers for Vision. So here, this bootcamp is planned to start on September 27th. So far in the current bootcamp, we did not discuss about transformer architecture, which also runs LLMs. But this is purely meant for transformers, not for text-based dataset though, for multimodal cases and vision use cases. This will, however, be a longer bootcamp, deeper and intense, 14 weeks. And structure will be once in a week, we'll be meeting on Saturdays from 10:30 to 10:30 a.m. to 12 p.m. You can check out the details. I'm putting this link in the chat. So check out this bootcamp if you are interested. I'll see you again. But otherwise, I'll be expecting to receive your submission sometime very soon. And I hope you enjoyed the bootcamp, and we can wind up now. If you have any questions or if you require any advice or any resources, feel free to reach out to me. I'm also putting my personal email in the chat. So you can just, this is my email. So you can reach out to me through this email. So thank you so much, everyone. We'll meet again in the next bootcamp. And if you need any comments or suggestions for these projects, you're welcome to ask or initiate discussions on Discord. The other thing is, I don't mind you working in teams also. If you want to work not as an individual, but as a team, I'm actually fine with that, as long as the contributions of members are clearly mentioned in the submission document PDF. So feel free to form teams and submit, no worries. But at the end of the day, I'll be evaluating based on the rubric for all the people in the team. So thank you so much. I hope you enjoyed the bootcamp, and we'll meet again in another one. Take care until then.